I think it's working. Hopefully. And this lecture, and also talked about the thermodynamics, basically the law, the ruler of all the molecules, how they behave, dynamics and things like that. Today, we're gonna continue on talking about this thermodynamics, getting in more detail actually. So, in the previous lecture, we talked about the first law of thermodynamics. Can anyone actually say in 1 or 2 sentences what the first law of thermodynamics is? Over there, back there. You gotta speak up a little bit.
Energy can't be created or destroyed, only converted.
Exactly. So everything is basically conserved and limited there. Nothing can be created. Nothing can be dissipated. Everything's there. It's just only about the conversion of the form, right? Can be heat, electrical, chemical, and things like that. And we talked about the some state functions like enthalpy, internal energy, and things like that. So let's keep just refreshing our sort of memories about these enthalpies and some other state functions. So enthalpy, which is basically the heat that is absorbed into the system, the energy form. It's a heat form, but it's actually the energy, right? Can delta H, the enthalpy change, tell whether the reaction is spontaneous? Can anyone answer to this question? I'm just trying to look for hold on. I was able to do that to get the laser. I mean, I don't know how to do that now. How did I do it? I don't remember. Thought I could find it here. Let's see. Right here. All right, that's good. So can anyone answer to this question? Can you tell whether, look at just the delta H enthalpy changes and say that this reaction is spontaneous or not? Is it yes? Why? That's okay. Any other person? It's okay. I mean, it was brave. I actually like that. So, anyone else? Because I've seen some hands raised, the first. So, I mean, when you just think about the energy changes, enthalpy, of course, that's the energy, basically the total energy that you're getting inside the system, right? So, the fact that there's a changes in enthalpy, you can actually should be sort of predict if the reaction actually goes on or goes backwards and things like that. It's sort of natural, right? But it's not. So here's an odd example I said. So that's using an ice pack. When you look at it, the dissolution of the urea or its ammonia nitrate, that process is endothermic, meaning that you're actually absorbing the energy, right? That's why your ice pack is really cold. So in theory, you're actually gaining the energy, but this process is actually spontaneous. So it really doesn't make sense, right? You're gaining on energy, but it's happening by itself. Why? So enthalpy is positive, but it's working. So why is it so? Because there are other state functions that are involved for this, basically telling the spontaneity of the reaction. And that's an entropy, which is a really important state function for the second law of thermodynamics. So today we're going to start with the second law of thermodynamics, which basically talks about the spontaneous process, how it works. And it's pretty simple too, as the first law. So it says the spontaneous processes are characterized by the conversion of order to disorder. So basically everything in the universe, I'm talking about the universe, not about just a isolated system or things like that. I'm talking about the whole thing. When you look at it, all the molecules and stuff like that in this universe should happen from the ordered form and move to the inordered state or disordered state. And that means entropy, which is basically tells about the disorderness increases. So it always happens in a way that the smaller entropy to the larger entropy. And of course, I mean, that could not happen actually. Something backward happens, but it's only the isolated part of the universe or the part of the system. And there always has to be followed by some kind of compensation where other regions, there's an entropy increases, or the other region, there's an energy changes there that compensates what is happening in the isolated system that is sort of abnormal. So we use term W to basically define disorder. And that is the measure or the measurement of the number of energetically equivalent ways to arrange the system. So that means, let's look at, take a look at an example here. There are two bulbs that are connected to each other. And in the middle, there's a stopcock there. And there is stuff inside just the one bulb. So that's there. Let's say that that's some kind of gas molecules. And once you release it by turning the stopcock here, then all the molecules here will naturally kind of diffuse to the other region where it used to be pretty empty. So that means now you're creating an environment where there's more of disorderness there. And that is what it's actually saying about the entropy here. The entropy increases. And when you consider the number of energetically equivalent ways to arrange those molecules, think about that. You have a smaller space here, and you have a certain number of molecules here. So there are going to be certain, almost like infinite number of, but still restricted in this space, number of ways to put those molecules in different ways. But now you have at least twice much of that combination here because your space suddenly increased to twice much, right? So basically, your number of energetically equivalent way to arrange the system increases by twofold or so. So your disorder also increases there. Again, entropy is about the degree of randomness or disorder. And this S, the entropy, can be defined by this equation here, which is entropy S equals KB, Boltzmann constant, which was coined by Ludwig Boltzmann. And he empirically actually measured this value of Boltzmann constant by comparing all different kinds of molecules and the different species and things like that. And then got this number, which was really useful now for us to get this entropy value. And also, it's going to be the product of this Boltzmann constant and the natural log ln of W, which is disorder here. And Boltzmann constant is in the unit of joule per K, Kelvin, because when you think about this entropy, it actually depends on the temperature. Because when the temperature increases, you can easily imagine that all the molecules are suddenly acting more actively, right? Brownian motion increases, and the volume can increase too. So it actually changes quite a bit of this entropy. So that's why S depends on T, and that's why this Boltzmann constant includes this Kelvin, the temperature measure in Kelvin in its equation. So by the second law of thermodynamics, which basically talks about everything move from the orderliness to the disorderly. If spontaneous process happens with the delta H equals 0 and delta U equals 0, and hopefully you guys still remember what those means. I'll get to that. Delta H is the enthalpy change, and delta U is the internal energy change. So both changes were 0, meaning that nothing really happened there, right? In this situation, which is sort of a normal situation within the system or the universe, then naturally you're going to get a positive value for delta H. The entropy change will be positive because everything moves from order to disorder. What is your question? That's a good question. So it's almost impossible. So we have to just deduce from other things. So what we're learning today is basically learn the way to estimate or to calculate those disorderedness, like the entropy or W, from the other equations, other measures, the state functions and things like that. So, but there's no way to do that directly, because it's impossible. I mean, if you're God, you can. You can count the number of possibilities there and just to come up with a certain, like a huge number, right? But it's impossible for humans. Any other questions? Okay, we're gonna move on. So like I told you, in natural conditions where there's no energy input gain or the, any kinds of like loss, then you're gonna always get the delta S as positive. But a process can still occur spontaneously even if delta H is positive. So again, if delta H is positive, that means you gain energy, right, or heat. So that reaction is basically endothermic and enthalpically opposed because basically the enthalpy increases, and that's something that is not desirable in terms of your reaction, right? You require something to make it happen. So that's why it's enthalpically opposed. But this can still happen only when delta H is positive, and also it is really large enough to outweigh the delta H changes. So again, going back to the example of ice pack, it's the endothermic process. So you're gaining the energy from the environment or the surrounding. So it doesn't look like it's kind of natural. It shouldn't be spontaneous process, but it's still occurring, right? You don't need to heat it up, ice pack, to get it to work, right? Why? Because there's a ammonium nitrate inside of that, which is separated from the water in the ice pack. And once you break the little package there, now the ammonium nitrate will be dissolved in the water. That means that but it also sucks up a lot of energy. So it seems like it's kind of undesirable condition, but actually this is like a totally separate two regions, water and the chemical urea kind of things. And then it dissolves in, now it spreads everywhere. So you actually gain a huge amount of entropy there that compensates the delta H change. Would that make sense? So when you talk about the entropy in biology, especially in biochemistry, you cannot measure W, like I told you. It's almost impossible. But we have actually other expression from the canonical or the classical thermodynamics definition, which uses the T. And again, in the biology, we typically have a pretty constant temperature, right? So that definition for delta S, the entropy change, is basically larger than or equal Q over T. And Q, as you can remember, hopefully, from the previous lecture, is a heat that is gaining into the system. So the system gets this amount of energy, the heat, right? That's the energy, but in the form of heat, and that's Q, and divided by T, basically temperature. And typically in biology, the pressure is constant. So it can be written as delta S larger or equals QP, which is the Q, the heat, at a constant pressure divided by T. So here's another question. Then can we predict the spontaneous reaction or not from looking at the entropy changes? Anyone? Why not? The textbook says so. Good answer. But a little bit more detail would be nice. Anyone? Pretty apparently, you already you studied about this even before. So the answer is no, because I mean it's kind of natural to think that now entropy is important, right? It's driving the ice pack working, so it's probably an important thing, right? It is an important thing, but there are other state functions. So here's an example again. Let's consider that there's a reaction where the two molecules of a hydrogen gas and one molecule of the oxygen gas becomes the two molecules of water molecule. And when you look at it, it actually happens spontaneously. But in terms of entropy, there's a decrease of the disorder. because there are 3 molecules started with, and then it becomes 2 molecules, right? So it's a smaller number, meaning that there's more orderness there, and it's not great in terms of entropy. But why is it happening there? The solution of this problem will be, we go back to this equation or the expression where delta S is larger or equal QP divided by T. And then hopefully you can remember the equations that we talked about, especially for the enthalpy changes in the previous lecture. Delta H equals delta U, internal energy changes, plus the work is done into the system, P delta V, right? And P is constant because we're talking about the biological system here. And this delta U is also can be written as this one as QP, the heat that is gained at a constant temperature, minus the work is done, there, W. And this W is the same as P delta V. We already talked about this. So hopefully this is not something really surprising to you guys. So that means, these guys cancels out. You ended up having just a QP. So that means delta H, the enthalpy changes, is the same as the heat gained into that system at a constant temperature, constant pressure, actually, not the temperature here. So you can just simply replace this QP with delta H to get this delta S larger than or equals delta H over T, especially at a constant pressure. And you can rearrange this. I mean, hopefully you guys can just process this because hopefully it's a simple algebra. So move this T and rearrange this H and S and things like that to ended up getting this delta H minus T delta S is smaller than 0. Are we following this? Does that make sense to everybody? All right, because this is really important. So in any kinds of spontaneous reactions, all the spontaneous reactions should meet this criteria where delta H minus T delta S is negative. And this is a true criterion for spontaneity of the reaction that you're looking at. And that was figured out by the J. Willard-Gibbs. And this J. Willard-Gibbs basically used this simple formula here, or the equation here, and introduced a new state function called Gibbs free energy, and it's written as G here. It's just simply just using these two state functions and the temperature here. So G, the Gibbs free energy, equals H, enthalpy, minus the product of temperature and entropy. And of course, you can look at the changes of the Gibbs free energy delta G. It's going to be putting the delta for the both state functions, right? And of course, like I told you, for any spontaneous reactions, you must get this value as negative, meaning that delta G, which is the same as this right here, should be negative. So let's take a look at those state functions just one by one now. Here's again delta G, Gibbs free energy change, equals delta H minus T delta S. And when you look at this delta H, if delta H is positive, that means the system absorbed energy. It gained some kind of energy there in the form of heat or something else, anything. And that means it's an endothermic process. In contrast to that, if delta H is negative, that means system loses energy, so it's exothermic process. When we look at the S changes here, the entropy change here, if delta S is positive, that means disorder increases. Again, entropy, the higher entropy means that there's more disorder. As opposed to when delta S is negative, that means the disorder decreases. And again, spontaneity of the reaction depends on delta G, basically here. That has to be negative. That means this spontaneity of a reaction or the prediction of that also depends on the delta H and delta S. So we can actually make a different sort of scenarios here of the delta H and delta S, two state functions, to basically tell that if delta G is positive or negative. And that also connects the prediction for that particular reaction, whether that is spontaneous or not. So let's take a look at the first scenario here, where delta H is negative and delta S is positive. So let's apply those, to here, the equation for the delta G. Delta H is negative and delta S is positive. Then this term will be negative, right? Negative plus negative. So delta G is going to be always negative. That means this reaction is always spontaneous. When you look at each state functions here, delta H is negative, so that means enthalpically favored, meaning that that's exothermic process. And when you look at delta S is positive, so it's also entropically favored because the entropy increases. There's more disorderly after the reaction. And this spontaneous reaction is called as exergonic process. So should you not be confused with exothermic and exergonic, because they're vastly different, as you can see. And exothermic or the endothermic is basically talking about energy that is gained, heat that is gained or not, as opposed to exergonic or endergonic, or for the spontaneity of the reaction. So again, this is for the enthalpy, and this exergonic or the endergonic process, and the definition of that is related to delta S, or the delta G, delta G for here. Let's look at the bottom case here, where the delta H is, I should actually show you this, delta G is always negative here. Delta H is positive, delta S is negative. That means this is positive, this is negative, but there's a minus, so that's going to be positive too, meaning that delta G is always positive. So that's going to be enthalpically and entropically opposed. And of course, that's going to be a non-spontaneous process because delta G is positive, basically, and it's called endergonic process. And there are two different cases here, right? Let's look at the third one here first. Delta H is positive, and delta S is positive too. Let's take a look at it. Delta H is positive, delta S is positive too, in which case, now you have to just compare these two terms, especially delta H and T delta S, right? This T delta S has to be bigger than delta H to get the negative value for delta G. Is that correct? So here, basically, delta H has to be smaller than T delta S, and you can just basically flip it over and just rearrange to get the T has to be larger than delta H over delta S, and that's what it's saying right here. So, and of course, delta H is positive, so enthalpically opposed, and endothermic process. But the delta S is positive, so entropically flavored, not flavored, favored reaction. Here, for the both state functions negative, then now you need to decide again. You're going to apply the same thing here, right? But when you're actually making this T, delta S moves to the other side of this, what is it? How do you call it? Just delta, basically intermediate step right here. And then since this delta S is a negative value, you're going to have a flip the relationship here. That makes sense? So now instead of temperature above this, you're going to have temperature below delta H divided by delta S. Does that make sense to everybody? All right. Move to the next one. So here's a quick summary. I mean, it's didn't take much time, but we actually covered a lot of things here. So spontaneous process is exergonic, and that means delta G, which is the true criterion to tell that the spontaneity of the reaction is negative. Just hold on a second. And the non-spontaneous processes are endergonic, meaning that delta G is positive. What is your question? So in the natural condition, let's say there's a reaction going, right, in the system. The natural setup or condition will be that it actually loses some heat, loses energy, rather than gaining some energy to process that. Does that make sense? Because it's independent system. When you actually lose the heat or the energy and do something, you can do it on your own, as opposed to if you require some energy or heat to process something or move forward for that process, then you always have to wait until that you get that enough energy, right? So enthalpically favored is meaning that you don't need to gain something. You don't require any other energy input at all, as opposed to enthalpically opposed, meaning that now you have to get something to move on, move forward. Does that make sense? And same thing applies for the entropy too. Any other questions? All right, so keep going. So for any reactions, especially for biochemical reactions, it never happens just one direction. It can actually go backward too. And when you look at that kind of reversible reaction, it'll be always exergonic in one direction and endergonic in the opposite direction. And it's kind of natural, right? Because you lose some heat or energy for a certain process. If you want to go back, reverse, then of course you have to gain the same amount of energy to get that initial state. If the reaction is at the equilibrium, meaning that looking like it's all kind of stalled, nothing's moving, but actually there could be some dynamics going on, but the end results are the same, right? There's nothing changed. There's a certain like products there, some reactants there, nothing changes in terms of concentration or anything. That means delta G equals 0. So there's no Gibbs free energy changes there. That's why it just looked like it's stopped there. And thermodynamics does not tell anything about the rate of the reactions, which is more involved in kinetics. And we're gonna discuss these kinetics and catalytics and things like that much later of this course. And if delta G equals negative, it's the same thing. This does not mean that the reaction will occur with the rapid speed or rapid rate. So an example is a diamond that turns into graphite, which is kind of a sad story, actually. This process is exergonic, so it can really happen, without any energy input or so. But the rate is almost infinite. It's infinitely slow. So basically, you don't need to worry about your diamond, turning into a kind of black gooey thing. So far we talked about the 4 state functions: U, H, S, and G. What is U? Internal energy or potential energy. What is H? Enthalpy. S? Entropy. G? Gibbs free energy. So those are the key state functions to understand the whole reactions, how it occurs, how much of energy has to be input or output and things like that, to understand everything biochemically. And these are independent of path that they took to get to that state. We only care about the initial state and the final state. And the same thing applies to the changes of these 4 state functions, which are delta U, delta H, delta S, and delta G. You can measure them. There are tools that you can measure. It's sort of relative, right? Although you can't measure the absolute value right there, but you can measure how much it changes by deducing, using some formulas or equations, or you can measure it directly too. And also these values, the delta values, are independent of the path that those reactions take. So again, only we're cares about the starting and the final stage. So here's an example of the glucose, and that breaks down to the carbon dioxide and the water molecule. And that's basically, it's called the glycolysis. And sort of a digestion step to gain the energy inside the cell. It's not actually digestion, but it's happening inside the cell to break down this glucose, use it as an energy source. And that happens, you can write it down as in this formula, basically here. And we also measure the amount of energy that is released, which is quite a lot here. So you can say that basically this is the initial stage, and this is the final stage, and you have this much of energy here. So since it releases the energy, the delta G is negative with the same number of amount of energy that is released. But actually, it is really impossible to precisely measure the delta H for the multiple steps there. So it's not just a single step. It happens a lot of different processes involved there for this glycolysis event. It's really hard because every steps have its own sort of little mechanisms there. And you can't really see the intermediate stages too well, especially inside the cell. And the energy is released gradually. Of course, there are multiple steps there, so it's hard to just keep following that, all the stages there. And also, there are other biochemical reactions can occur at the same time inside of the body that also releases energy, absorbs the energy, and things like that. So it's really hard, actually. But you can still measure some simple reactions like this using the tool called the bomb calorimeter. And this is basically looking like the little chamber. And inside of that, there is a water, and there's a smaller chamber there where you can put some substance that you're testing. And basically what you're doing is just burning it all the way. And measure the temperature changes there in water. And by the temperature changes, you can tell how much of energy, basically heat, released there to calculate the delta G there. For this delta G of the reaction, especially when there are multiple products, multiple reactants and multiple products are involved, it might be hard to even do the calorimeter, using the calorimeter to measure those values. But there are, like I told you, you can break them out into the separate steps, and each steps you can actually use the calorimeter to measure the delta G, the energy changes there. And there's a table of that pretty conveniently already there. So you can actually use these tables and can calculate the total delta G, the Gibbs free energy changes of the reaction that you're interested in by using individual delta G values that for the reactions. You basically add up all the delta G from your products and subtract it with all the sum of all the delta G values from your reactants. And you can simply imagine that it's all about final and initial stages, right? You don't care about the intermediate stages. So there's a certain state, and you can get the delta G values there. It's all about the energy transfer, right? Going from the one molecule to the other molecule. So everything's additive. For delta G, there's an alternative way to calculate it. And for that case, we use KEQ, which is an equilibrium constant. And also it's called the dissociation constant at equilibrium. It is a pretty actually simple term, as KEQ equals the concentration of all the products divided by the concentration of all the reactants. So it's just a ratio of the molecules that you're having, starting with and ending with. And the G, the Gibbs free energy, is related to the concentration of these reactants and products. It's kind of hard to imagine when you look at it. Let's go back to the delta G equation here, where delta G equals delta H minus T delta S. There's nothing about the concentrations or even products or reactants. But going back to this example where there are two bulbs that are connected to each other, when this stopcock is releasing this gas from the one chamber to the other, now the concentration immediately changes, right? It decreases. Naturally, decrease of the concentration leads to the increase of entropy. So it directly affects the entropy change. And of course, entropy changes will affect the delta G there. So that's why the concentration of the reactants and products are important and related, directly related for delta G, or even just a G, Gibbs free energy. So when we make the relationship between the delta G and KEQ, we use other definition of delta G, where delta G equals delta G naught, and here G naught, meaning that it's delta G, Gibbs free energy change, at the standard condition. And we're going to talk about the standard condition in a minute, plus RT multiplied by natural log ln, and the concentration of the products divided by concentration of the reactants. And if you are familiar with some physics, gas, energy, and their potential energies and things like that, you probably are familiar with this to RT ln and the concentration ratio. So we bring the same concept here and convert it into, because this is a form of energy, we just convert it into the Gibbs free energy with the starting point at the standard state. And the ratio of the products and the reactant concentration is basically the definition for KEQ, which is right here. So it can be written as, it's pretty much the same here, delta G equals delta G naught plus RT ln KEQ. And here R is the gas constant. So let's consider there's a reaction where A number of A molecule, B number of B molecule becomes C number of C molecule, and D of D molecule. And then there are concentrations there, right? So you can write the delta G as delta G naught plus RT ln, and the concentration of all the products, which are C and D, and the concentration of the reactants, A and B here. And keep in mind that this is where the reaction is initiated and is happening. So it's different from the state where it is at the equilibrium. So we're not talking about A, B, C, D, the stable values, the constant values. We're talking about the start point of the reaction. So it's not going to be simply just a 1 or something like that, some simple number. And again, like I told you, delta G naught is the delta G at the standard state. Then what is the standard state? Standard state is where chemists define that this is sort of the ideal condition, that everything can be in the simplest form or simplest ratio. And that is where the pH equals 7, and temperature is 25 degrees Celsius or 298 Kelvin. And all the reagents should present at 1 molar. And I don't know if you have the concepts of the molar concentration or molar ratio, but 1 molar is a really high concentration, high molar concentration. So it's almost impossible to get it in any kinds of biological system. But anyway, that's the chemist's standard state definition. So let's imagine that you have this reaction AB and CD, and you're at the standard state, then all of them should be at 1 molar. So 1, 1 divided by 1, 1 here. So that's going to be basically ln1, which becomes, what is it? What's the number? What is ln1? 0, right? So basically, this one goes away. You're going to end up having delta G equals delta G naught. So delta G naught is delta G Gibbs free energy at this condition with everything at a 1 molar. Okay, I talked about this. And delta G naught is constant value because this is ideal condition, only one condition, right? The state. As opposed to here, we're talking about certain stage, certain different state. So these concentrations can vary. So here's another question. Can we predict this certain reaction is proceeding spontaneously, even if its delta G naught value is positive? That makes sense? Delta G naught is important, right? That Gibbs free energy changes at the standard state. And delta G can tell that if the reaction is spontaneous or not, right? Can we tell that if the delta G is positive, then this is spontaneous? We have formula here that we talked about. Anyone? Yes or no? Yes? Why? It's okay. Trust me, you're not gonna look dumb or anything. So
Like the delta G that we have, if it's still negative, then it can still be spontaneous. So as long as that's not beneficial.
you actually got that. Well, the answer is yes, because of this value, right? It's not just simply this delta G, but there's a RT, ln, and then KEQ. And depending on this value, if that is negative, or the positive, it can actually skew, or not really skewing, but change the delta G value. So you have to look at this term to tell that if this is spontaneous or not. So this, again, like I told you, only this happens, the spontaneous reaction only happens when delta G is negative. So that means this RT, ln, KEQ, the ratio of the concentration of the product and the reactants should be sufficiently negative to outweigh the positive delta G naught to make this process moving forward. And this is when do you get this RT, ln, KEQ really sufficiently negative? That's when you get this ratio of, again, the concentration of the product and the concentration of reactant very small. And you can just simply see that for this natural log. And as you know, natural log is having the base of E. So that's log EX. And this is the plot that you can see, simple plot. And of course, ln1 equals 0, right? Yx here. And when it gets really small, then you have a really high negative value, meaning that you're going to have a really large negative value here that can hopefully outweigh this delta G naught to make this reaction happening. Make sense? Then can we get the even negative value for this ln x? Can we get that value? So it's showing until here, right? If it is a negative value, that'll be even better, right? Do you think you can get any negative value for this x? And x is, again, the ratio of the concentration of the products and reactants, or the KEQ. Can you get the negative value for KEQ? Anyone? Why not? What is it? KEQ, I don't think I catch it. Right, KEQ. My question was that KEQ, whether KEQ can be negative or not, right? No, because, I'm sorry, I didn't hear you. Because the product always is larger, the concentration of the products is larger than the concentration of reactants. That was the answer? Exactly. It's simply just a negative value comes from the some kind of negative concentration somewhere, right? But doesn't mean that you're wrong. I mean, that definitely determines the value for that log function. So that is really important. But basically, you will never get negative value here. So I might just ask you, something like a multiple choices. If KEQ is -1, you just simply think that it's impossible, right? It's not going to be the right answer. Does it make sense to everybody? There's no way to have a negative value for concentration. If and also this one can happen where you have a really small ratio of the concentration of the products and the reactants when you just get rid of C and D, the products, immediately. when they are produced. And that's where the reaction, there's another reaction actually using this CND as reactants, right? In this case, the product's concentration will be still kept low, right? So the delta G will stay really negative value because this one keeps as the low value there. And then the reaction can just keep going. And that's what sort of most of the biochemical reactions utilize, actually. So, because there are not such thing as there's always a high delta G, really low delta G there, that the reaction is always ongoing. If that is really happening in your body, you're gonna have some trouble. Let's think about that. Something is going on, keep going until you just consumes all the energy. So there's always a balance. Delta G is a little bit negative or a little bit positive depending on the setting. But to make it like boosted, you need to do something on there, right? And the most of the biological reactions is happening where it changed the ratio of those concentrations.
So you're saying that
That's correct, actually. So it's much ahead, actually. When we look at just the whole thing or the certain stages, there could be some equilibrium there. But when you look at it as a sort of the process, all the process is going on, then it's never going to be at equilibrium because there's always some steps some dips and ups and things like that in terms of energy usages. So this is much advanced. So we're going to talk about this much later of this course. So I don't want to say too much about this. Go ahead. But in the end, it's all about the equilibrium. That's correct. Any other questions? Sorry, I only heard human body, so can you speak up a little bit? That's a good question. So, I mean, in the end, we want to keep at a certain state, right? Happy state, if you will. It's called a homeostasis, basically. You want to keep it at sort of a cool, nice, relaxing condition there. But it's different from equilibrium. Equilibrium is more like the reaction itself, right? Reaction can just keep going, right? And equilibrium is all about that initial and final stages, not about what is actually going on there. So it's a little bit different. If you reach the equilibrium without any kinds of reactions going on, it's a dead body, basically, right? So it's a little like a different definition there. But human body can reach equilibrium, not as a whole body, but some of the biological processes. So we talked about that, and we're gonna basically look at those things. But it has to be followed by the constant energy input, right? If you have like a limit in the energy input, or if there's a changes, then of course you're not gonna reach the equilibrium. Then you have to do something to get to the second equilibrium state, or recover back to the first stage. All right, so at the equilibrium where the delta G equals 0, basically, all the concentration of the reactants and the products are constant now. That doesn't mean that there's no reaction, right? There's always a reaction there. It's pretty dynamic, but there's the same amount of reactants become product, and the same amount products becomes reactants, goes back to reactants. And that means that you reach the equilibrium constant, which is KEQ. Now, you can say that the concentration of the C and D divided by the concentration of A and B, the reactants, is the same as KEQ. And it actually has to be written as this. This is the most precise way. But during my lecture, I'm going to just omitting this EQ many times. And when you substitute this KEQ with this CDAB concentration ratios that we talked about, the equation that we talked about in the previous slide, what you're getting is going to be delta G is going to be 0, right? Because it's at equilibrium. And there's a delta G naught plus RT, ln, and then KEQ. And then again, you can rearrange this equation basically to get the ln KEQ equals minus delta G naught divided by RT. And also as a definition of the natural log, you can take out KEQ, which is going to be the base of natural log E to the minus delta G naught divided by RT. So this is delta G naught actually. I have to change it. This little O should be on the top right here. And this is a really important relationship. Looks like a little complicated, but it's actually really important because now you can see the direct relationship between KEQ and delta G naught here. So that means if you know KEQ, you can calculate back the delta G naught and vice versa too. So here again, the relationship between KEQ and delta G naught here. And of course, it can be written as this too, right? It's the same thing as minuses here. So you can just take it out as this one. And the consequences of this relationship would be that if there's a small changes in delta G naught, since this is on the exponential function, you're gonna have the huge changes in KEQ. But even if you have huge changes, large changes in KEQ, that doesn't mean that you're gonna have huge change in delta G naught too. So here's again the reaction AA plus BB that gets to the C and D as products. And this is the KEQ definition here. If delta G naught is large, so delta G naught is really large and positive, that means you're gonna have a really high value here. And since this value is in the denominator, you're gonna have a really small value of KEQ, right? And small value of KEQ, that means you're gonna have a lot of A and B, but little of C and D. Would that make sense? So you're gonna end up having your reaction going more like this direction to reserve or produce more A and B. So the reaction goes to the left of this. And that's reverse reaction, basically, which is favored if this occurs at the standard state. Make sense? And in the other way, if delta G is large and negative, think about that. This is large, but it's negative. Then you're going to get the really high value for KEQ, right? So KEQ is large. That means you have a lot of C and D instead of A and B. So the reaction goes right, like that, producing C and D. So that's going to be a forward reaction that is favored at the standard state. Here's a little like a simple table comparing the KEQ and the delta G naught relationship here. As you can see, there's a small changes in delta G naught that drives the huge changes in KEQ. Again, the same question. Can you get the negative value for KEQ? No, because this is the ratio of the concentrations. So you're going to have really, really small values, but still positive. But in the cell, let's think about the cell. The actual delta G and the direction of the reaction depends on the actual reactants and the products concentration rather than the KEQ. So, because we talked about a little bit, but for the reaction that occur, you shouldn't be at the equilibrium, right? You should be out of equilibrium to force it to get to the equilibrium. So again, instead of using the KEQ, it's going to be almost always delta G equals delta G naught plus RT ln and the ratio of the concentrations of the product and reactants. Now, let's even go further and determine delta H and use the delta H and delta S to see the delta G using the relationship of delta G naught and KEQ that we talked about. I know there are a lot of formulas and equations and things like that, but in the end, it's going to be really helpful for you to understand the spontaneity of the reaction. It's all about the reaction and how much of energy is involved there, whether that is input or output. So we have this again, delta G naught equals minus RT ln KEQ that we actually got from the a few slides back. And when you rearrange this ln KEQ, it's going to be minus delta G naught divided by RT. So simply just moving this minus RT right here. And remember that the definition of delta G was that it's delta H minus T delta S, enthalpy changes minus temperature, and the entropy changes. And at the standard state, it's going to be basically you're just putting knots in front of in the end of all the state functions. So delta G naught equals delta H naught minus T delta S naught. And now let's substitute this expression with the above here, ln KEQ. So ln KEQ, and there's a delta G naught, and just replace it with this delta H minus T delta S. And you just rearrange this to get this ln KEQ equals minus delta H naught divided by RT plus delta S naught divided by R. And looking like a little complicated formula, but it actually is a sort of a simple linear function where the y equals ln KEQ, k equals minus delta H naught divided by R, and x would be the inverse t, and b, the interceptor, would be the delta S naught divided by R. Any questions so far? Okay, so again, this is the the last equation that we got, and it exactly looks like the linear function here, y equals kx plus b. And again, like I told you, the y-axis, the y function, the variable would be ln KEQ, and x variable would be the 1 over t. And we can also determine the slope of this linear function by looking at the coefficient of x, right? So just again, simple algebra, where the slope is the same as k, which is minus delta H naught divided by R. And that means when we get this linear function, if we can determine the k and b here, we can basically tell that how much of delta H naught is, because R is the gas constant. It's the constant value. So you can simply calculate the delta H naught there. And also you can get the intercept, y and x and y intercept too, right? Which defines the b. And sometimes that is plotted as R by moving this R on the denominator to the other side, and the function of inverse t too, but it's the same thing. And this function or this plot is called as Van't-Hoff plot or Van't-Hoff plot. And basically this is for determining this slope and the delta H. If you know this temperature and the corresponding KEQ. Do you think you can measure KEQ? Can you measure KEQ? What do you think? Again, yes or no? Anyone? It's just a yes or no. Make a wild guess, it's fine. No, why not? It's okay. If it was a wild guess, that's fine. Somebody said yes. And why so? You can just let any reaction happens, and just wait for a while, let's say a day or two, maybe a month or so. It should be at the equilibrium state by then, right? And then now you just take up those chemicals and measure the concentration, that's all. So you can do that. You can measure KEQ. Can you measure temperature? Yes, you can. So those are all the measurable values actually. So you can get as many dots as possible, and then you can draw the line there. Once you have line, then you can deduce the linear function, right? Basically getting the slope there, where you can predict the what delta H naught is. It's all about measuring the enthalpy change, and that is important because that is how much of energy the system gained or loses basically. Now let's go back to the standard state here, and like I told you, the chemists use standard states with these conditions where temperature is 25 degrees C or 298 Kelvin, pressure is 1 atmosphere, and the all reagents have to be at 1 molar. But us, we biochemists use a different definition for the standard state because this is nowhere closer to the what is really happening, what the conditions really have inside the cell. So, and we also used a slightly different notation as delta G naught prime, but it's not so convenient, right? So during this course, I'm gonna just call it as delta G naught, but always I'm referring the biochemist's standard state. And the differences between the chemists and biochemists' standard state is that for the biochemists to use the activity, same thing as the concentration. And hopefully you know the definition of activity from the chemistry course or the organic chemistry, which basically talks about the effective concentration. So the concentration is dependent on the actual current concentration. If you have a lot of stuff already there, then it can have pretty effective, like any kinds of affecting the reactions and things like that, as opposed to if you have a little of them, it basically have a little effect, right? So you have to normalize that to have the actual effect of the concentration of all the molecules for the reactions. So since all the reactants and products in the cell or any kinds of a biochemical system is pretty low in millimolar, if not micromolar ranges. So they're pretty low, so you can actually consider activity as concentration as it is. It's pretty safe to use that. And the activity of a pure water is assigned a value of 1. And that actually doesn't make sense because the concentration of water is 55.5 molar. But using 55.5 is pretty inconvenient for the biochemical reactions because you always have to divide it by 55.5. Everything happens in water, right, in cell. So instead of using that weird number to us, why don't we just use number as 1 for that? So we ignore that value. And the H cation activity is set to 1, even at the pH 7. So it has to be pH 1 where the water cation concentration is 1 molar. So that's where activity is 1, right? But since everything is mostly happening at pH 7, we use this 1 at this condition. And also the ionizable substances, even if they can be ionized in many different forms, complete or incomplete like that, we just consider that as the whole thing that is happening one species at the pH 7. So making things a little bit simpler than what chemists use. And change a little bit of condition to make it more like a better fit to the any kinds of cellular systems here. And again, remember that the delta G predicts the spontaneity of the reaction, but does not say anything about the rate of the reaction. Here was another, again, the same example where glycolysis happens. So glucose breaks down to the carbon dioxide and the water molecule here. But when you look at the glucose actually in the lab on the shelf, it just stays there constantly. And that is, although it actually has a really negative value for the delta G because of the rate is really slow. So you can actually safely store that at the room temperature. Same thing for the diamond and the graphite, like I told you. Again, you don't need to worry about your diamonds if you have one. I don't, so anyway. But actually, there is another process that is involved for changing or regulating the rate of the reaction. And that's done by the catalysis. And the catalysts basically, which utilize the catalysis, changes the rate of the reaction. So it can go faster, slower, things like that. But catalysts actually do not change the delta G value. So biochemist's view of thermodynamics is basically a little bit different from the physicists' thermodynamics. We believe that the life, as well as all the molecules involved in sustaining the life and the perpetuating life, like biomacromolecules and things like that, obeys the law of thermodynamics. And living organisms require energy, of course, so it needs input and output of the energies. And biochemists study the processes by which the energy is extracted, channeled, consumed, gained, transferred, converted by the living organisms. And thermodynamics, basically, which talks about the bioenergetics, how energy flows, right, gives us the way to describe and characterize the energy changes in any biochemical reactions. And that includes the plants and the animals and things like that. What they do is basically gains the energy in any kinds of forms. It can be just radiant energy from the sun. It can be something like you're eating, consuming, things like that. And of course, you lose this energy by heat loss or some other things that you secrete too. But in the end, that's gonna be all sort of in the homeostasis, like I told you, like sustaining the life as it is, involved with a lot of biochemical reactions at the equilibrium state, as well as something not too. And what we are trying to do in this biochemistry class is to understand all these phenomena, how they survive in the terms of chemistry using thermodynamics again. Here are the quick summaries. First one is the energy, internal energy, delta U is the U final minus U initial, Q minus W. Enthalpy, we already talked about that. Delta H equals delta U internal change and the work. And delta H is basically same as Q at a constant pressure. And the entropy, we talked about that using the Boltzmann's definition, as well as some other classical definition too. Free energy delta G is delta H minus T delta S, and which is a criterion of spontaneity. And you can predict the spontaneity using the delta G, but you can't predict the rate of the reaction. Delta G has to be negative for the reaction to go forward, right? Just a quick summary too. This is the last one. And the reason that I'm putting these summaries is not for my lecture, actually, for you guys. So look at them, understand them, digest them, memorize them, right? It's all about the KEQ stage, the delta G value in different terms. And you can get the relationship between delta G naught and the KEQ. And we talked about the using the Bantoff plot for that. And energy, the free energy is additive. All right, that's it. Have a nice weekend.